Hello everybody, and welcome to the next installment of Dam Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, and just like in the last video, I promised you that I would tell you how to find the GM of a vessel just based on statical curve of stability. We're going to learn that in this video right here. Now, in deriving this, there is some high-level mathematics that I'm going to use. So if you really don't want to get into the weeds of this mathematics and just kind of hit the I believe button and say that if you take that line all the way to 57.3, that's the vessel's GM, that's perfectly fine. But if you are interested in exactly how it's derived, I'm going to go through that right now. So I mentioned before the stability triangle, and we're going to need that right now. We have the ship right here, and it's being inclined over some angle theta. As it's inclined, this GZ, this writing arm, starts to develop. As you incline over further and further, that GZ gets larger to a certain point, and then it starts to diminish as the metacenter moves along metacentric. We learned that the GZ, the writing arm, equals GM, the metacentric height, times the sine of theta. And if you remember from trigonometry class, theta is this angle here, and so sine is just the relationship between the opposite side and the hypotenuse. Is there a way that we can manipulate this formula here in order to make it something more clear that we can use on the statical stability chart? Well, there is. If we arrange it here, we see GZ divided by the sine of theta equals GM, and then just divided by 1. Now, what can we do with this? Well, we see here sine of theta. Is there any way that we can make this a little bit easier for us when it comes to the curve? Well, there is. Now, to make this easier on ourselves, we have to do what's called a Taylor expansion. Taylor expansion, you can find more information about it in YouTube or on some other textbook. But a Taylor expansion basically says that you can take any curve, whether it's simple or complex, and restate that curve as a summation of many different formulas or terms on top of it. So, for sine, I won't get into the definition of a Taylor expansion or anything, but a Taylor expanded sine can be restated as theta minus theta cubed divided by 3 factorial plus theta to the 5th divided by 5 factorial minus, and it goes on and on and on. A Taylor expansion is an infinite sum of different expressions like this. So if we think, so theta, when we're dealing with expansions and things like that, we have to be dealing in radians. Typically all engineering is done in radians, and this is no exception. So if we have theta, that's not necessarily going to be a very, very small number. However, if we have theta cubed and theta to the 5th and everything else, those are going to be small numbers and then multiplied by themselves several times. So those are going to be extremely small numbers. So if we keep everything as close as we can to the initial expression, which would be as close to 0 as possible, then we can just cancel out these terms. Which means that as long as we stay, it's called linearization, as long as we linearize sine using theta with very, very small thetas, then our expression won't be too far off. And we can see that right here. At 3 degrees, there's only a 0.04% difference between a line theta and then the sine of theta. We're talking about at 3 degrees, we're probably right around here. And then at 10 degrees, we start to get a little bit more divergence. 10 degrees is probably right around here. And you see here, the values are starting to go away from each other, whereas as close as you possibly can to the origin, that you're going to have a very little difference between sine of theta, which is the actual expression, and then theta, which is the linearized expression. All right, cool. So with that, we know that as long as we stay close to the origin, so in very, very small numbers of degrees, so maybe 0, 1, 0, 2, maybe even 0 to 3, then we can take that sine theta and just re-express it as theta. So we come back up here, but there's one issue that we have, and it's this 1. What does this 1 really mean? Well, if you take what I said before, we have to work in radians. 1 radian, and you can look up more about radians on YouTube or somewhere else, but 1 radian is going to be 57.3 degrees. Now that number isn't looking so random that I had mentioned before. So now we know that as long as we stay close to the origin, our sine of theta is going to look just like theta. And we also know that 1 radian is 57.3. So let's go to an actual statical stability curve. here's just an example of the typical look that you'll see for a statical stability curve. Now, I had mentioned you want to stay as close to the origin as possible. So let's just kind of zoom in on the small degrees here. If we zoom in, so here's our new set of axes. And let's say this is like 1 degree, 2 degrees, and 3 degrees. We see that this is a very, very straight line. There's very little deviation from it. And the slope of this line, if you remember from high school or math back then, the slope of a line is the rise over the run. As we go up, we have the GZ, the writing arm. And the run, the horizontal distance, is theta. And you'll see that here. We have the rise over the run. Now, if we know that this is the rise over the run, whatever it equals has to be a rise over a run. So the GM is the rise, and then the run would be 1, or 57.3 degrees. So now we can say, if we take this line that's originally defined as GZ over theta, which is this here, basically the statical curve of stability that we have at extremely small angles, and assuming that that is perfectly linear, if we take that line and just run it all the way out, wherever it hits that 57.3 degrees, or 1 radian, that's going to give us our GM. We take the rise over the run, then we just extrapolate it all the way the horizontal distance, and it's going to give us what our rise is. That rise being the previously defined metacentric height, GM. Now you've seen me use this already in the previous video. I'm just going to show you it again. So if you have a statical curve of stability, it looks something like this, and this is just going to be the typical look that any statical curve of stability will have. You want to take you just want to linearize as close as you possibly can to the origin. So I would say draw a point at 0, and then draw another point where the curve is at 3 degrees maybe. So say right here. You have your origin and then your 3 degrees. Then you can take a ruler or some sort of straight edge, connect the 2 dots, and then just draw a straight line. And then continue that all the way until you hit that 57.3 radian line. So here we see that they cross right about here. You read that off of this axis, which is going to be your GZ in feet, and then that number that you read is going to be the GM of the vessel. It's going to be your metacentric height. The next 2 videos are going to be about sine corrections and cosine corrections for where the center of gravity is on a ship related to the assumed center of gravity on a naval architect's calculations. When we have a sine correction, we can still use this radian line. However, if we have a cosine correction, we can't. And we're going to learn why and why not in these later videos. I would suggest if you're not very familiar with sine, cosine, or tangent, just go and look on other videos on YouTube and just kind of get back on that horse and remember back from high school trigonometry what these mean. That way, when I'm talking about them in later videos, you'll be right there with me. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.